Ooh, there we go. Okay, so we're recording, and I'll hand things over to Group 13 to describe HElIO 1.
Hi, thank you, Professor Chom. Good afternoon. Hello, we are HElIO 1, and we believe that we can produce a low-cost heliostat that can beat out other current models and other companies that produce non-reusable sunlight. Sorry, kind of choked. Thomas Gallagher.
I'm Nicholas.
I'm Nate Keys.
I'm Joshua Lin.
I'm Joseph Neighbors.
And I'm Will Thomas.
So I guess we're going to walk you guys through a presentation outline here. It's going to be short, maybe like 20 minutes. We're passionate in what we're going to do. We're going to go through a product overview, show you what it looks like, some key features, and why you should choose us.
So we really focused on 3 aspects for our design: passion, profitability, and expertise. We focused on our passion for developing green energy solutions to combat climate change, as we feel like heliostat technology is the future of clean energy generation. We also created a design that's able to be profitable, as our solution is very modular and low cost. So it's easy to develop large heliostat fields. And we also focused on our use of background research and prior knowledge to make the best possible design.
So this is our product overview. Now focusing on a functional heliostat that was modular. We went with something that was easy to produce. And with that, we found this design. So we focused on a 45-degree angle support system that allowed for the minimized shading, so that at sunrise and as well as like noon right above, there is no way the mirrors are going to shade each other. And we have 4 subsystems. We have a support subsystem, a reflection subsystem, electronic subsystem, and actuation subsystem. Now we built off from our support system. We started out with aluminum bar stock, which was very expensive, and we eventually got down to which the support system right now is that you're seeing is 1.5-inch Schedule 40 PVC pipe. This was both cheap and it was durable for the intended purposes here. And we chose that size and that material because it was strong. It would last the required 20 years that the customer wanted, and it was easy to put together. It just involved general stuff you buy from stores for connecting, and it made it lightweight. For our reflection subsystem, we have ABS backing along with a Mylar film to reflect the sunlight. Mylar film was chosen because it's cheap and we can get a lot of it, and it's easy to attach. It's adhesive to the ABS backing on the mirror backing. Sorry. For electronic subsystem, we did a normal high let go board, I believe, the 32 SP chip, and along with 5 drivers to power our 5 motors, which leads us to our actuation subsystem. We have 5 separate motors. The 4 separate motors on the mirrors control the vertical actuation, and the separate motor at the base of the heliostat controls the rotation of the entire module. We chose just simple separate motors because it allowed us to get within our accuracy of 0.25 degrees plus or minus, as well as it was low cost. We have a gear train that is led from the stepper motors that controls the mirrors. It's a 3.6-to-1 gear ratio, that I'll get into later. And the gears are closed. We have limit switches so that the mirrors can find home. And sorry, my mouse isn't working. Okay. So this is our field layout. Originally, we were going to choose a 360-degree field, but we went with a 150-degree field because we could get the required 1,000 concentrated suns within the 100-meter max distance from the central tower. We are at right now, the first row is 20 meters from the tower, and the last row would be 100 meters, depending on how many heliostats we're putting in. For our 1,000 concentrated suns, at a 92% reflectivity rate for Mylar, we calculated that 1,087 modules will be needed. The total volume for our module is 1 meter square or 1 meter cubed, which we focused on for a small modular design so that more can be placed in a smaller area. We allowed for a 0.5 meter between models to allow for movement of each one. Then it's relatively low space between each one. So it allowed for our total area for 1,000 meters be roughly 3,100 meters. And it's a lot of, you get the 1,000 concentrated suns in a low total area. So this is the better representation of our field layout, how it look. This is not the total 1,087 that we have prepared, but it's just a simple representation of what it will look like once together. It's an easy model. It's easy to set up. Everything can be in a line. And because of our small scale heliostat with a small reflection to support area and just a small volume in total, we can put a lot more heliostats in a lot smaller of a space. And here we're going to have a display of the vertical motion of our mirrors. Let's see if this works. And that's the max they go. It's around 180 degrees for the movement vertically and 360 degrees for the rotation at the base shaft. Oh, sorry.
Yeah. For subsystems, we have 4 tubes with the same inner and outer diameter. One of the main structure, and this provides a height of the tower around 0.5 meters. The other 3 tubes were put together by PVC group on the top in a H shape, and the top structure are angled into 45 degrees to avoid shading during sunrise and sunset. And why did we choose PVC tubes? It's because it is pretty economical and have a relative long life cycle under 50 degrees and high corrosive resistance and oxide resistance indeed. To avoid rising temperature from the sunlight, we also put UV coating on the surface of all the tubes. Okay, assumption that we made here, in order to do an analysis, we assume that there are 2 modes. One is regular mode, and this means factor of safety is designed around wind speed equals 35 miles per hour. And the other mode will be triggered if the wind speed is beyond 35 and the maximum is 95. The reflecting surface will be turned into certain angle, which is completely perpendicular to where the wind comes from to reduce the wind load. For each mode, we calculate shear stress, normal stress due to weight, and bending stress and buckling on a few critical points, like this slide show. We found that bending stress and buckling are the main 2 elements we have to focus on. Shear stress and normal stress all have factor of safety beyond 200, so we don't have to worry about that. For buckling analysis, one end is fixed in the concrete floor and the other end is free of movement. Next, we just plug in the values into buckling equation. One thing to be mentioned here is the tubes have outer diameter of 38 millimeter and 30 inner diameter. This gives us a relative small value of moment of inertia. We have to beware of, but yeah, the main downward force is caused by the weight of all components on the top, which we assume they are 2.5 kilograms each, and that includes all the cases, mount, bearings, and reflecting surfaces. The outcome shows the first critical load is around 380 newtons for a PVC tube tower with tall of 0.5 meters. Yes, 0.5 meters. This gives us factor of safety equals 3.2, and that is larger than 2, which is our customer requirement. And yeah, in safety mode, buckling is the same and regular mode, same as the regular mode, since a strong wind force will not apply any normal load to the top of the main tube. The next is bending stress. Since the bending stress is caused by moment, we can easily tell where the max moment will occur, like 0.1 and 0.2 in the slide. Next, we determine the force caused by wind. All assumptions were made by assuming the worst situation, like vertical to the wind and drag force coefficient of 1.1. And yes, let me take a look. Yes, that's the drag coefficient for a plate. And we found the outer surface of a tube will suffer a bending stress load around 19 megapascal, and the Young's modulus of PVC is 50 megapascal. So the result of factor of safety is around 2.5. This also meets the customer's requirement. For the next point, because on a point 2, because the load are the same and the difference is the length of moment arms, we found that max moment on the top will always be 2/3 of the moment on the bottom point, and all the other variables are the same, which means as long as bottom is safe, the top will be safe as well. So you can see the accurate value in the slides. And the next is safety mode. Under wind speed equals 95 miles per hour, just like the previous assumption, all shapes are considered as plate and vertical to the wind. More structure like protection case and tubes are put into our calculation. In this case, even though the area are small, but since the wind speed is larger, and according to equation, speed has power of 2. Thus, in this case, they are not ignored. The results are also shown in the slide. Factor of safety are around 4. In safety mode, like this is a little sketchy, but good enough. Okay, next slide, please. So one of the requirements for our customer is the space efficiency. In our original design, unlike this final design version, it has a long arm. 4 reflective surfaces are arranged in the same line, but we found that that would take too much space if the module start rotating. Yeah, so arrange in a square is better than a line overall. Yeah.
Okay, so for our actuation subsystem, this component here is focused specifically on the mirror actuation, which rotates the mirrors vertically. We have a stepper motor located on each mirror, and that connects to a gear train, which then attaches to a ball bearing with retaining rings to hold everything on. And we also have a limit switch on each mirror arm to make sure that the motor doesn't overactuate. So in specific, each stepper motor that we have moves at 1.8 degrees per step. We have a gear ratio of 3.6 to 1. So that means that the entire motor moves the mirror 0.5 degrees per step, which satisfies the need of a plus or minus 2.5% accuracy. Overall, to move the mirror, 0.9 revolutions of the motor are needed. even though the motor is rated for a really high RPM, we're limiting it to only 5 RPM because we don't need the motors to move as fast, which also improves the longevity of the design. So as talked about before, we have the safety position where the mirrors are moved from whichever position they currently are to completely flat, and that takes about 10.8 seconds moving at 5 RPM. Each mirror is capable of moving 180 degrees, which even though it might not necessarily need to move 180 degrees based on the field layout, it's still capable of doing so. And the base is capable of rotating a complete 360 degrees, which again, also might not be needed depending on the field layout. So we focused on the gears and motor shafts to determine the forces experienced by them. And we originally had steel gears, but when examining the manufacturing price, we realized that ABS plastic was a lot better to go with. So we focused on the small gears and calculated the max stress experienced by them, including a factor safety of 2, was about 8 MPa. And then for the larger shaft gears, it was 1.6, and that's after considering a factor safety of 2, which is less than the yield stress of ABS plastic. And we also did a similar calculation on the motor shafts, which were far from failing at any point.
All right, so here's our mirror subsystem. The Mylar sheet is backed with ABS plastic, which connects to the PVC pipe. Next slide, please. So the total reflective area for each module is 1 square meter, and with 4 mirrors per module, each one has an area of 0.5 square meters. The distance between heliostats was calculated to avoid mechanical interference between adjacent heliostats and also leave additional room for shading and blocking. So that is 0.5 meters. The height of the tower the receiver is 18 meters, which means that the inner radius of the field has to reflect the sunlight at a 42.77 degree angle. And those of the outer radius of the field have to reflect the sunlight at an 18.68 degree angle. So the reflectivity of the Mylar sheet is 92%. And the ABS plastic backing was selected from an Ashby plot to optimize the strength to weight ratio. ABS plastic was selected because it has a high enough strength to deal with the wind force, it's low weight, and it's low cost. For the washing and cleaning, the top equation is the cleanliness ratio, which is used as a parameter for the bottom equation, which is the swirling rate. The swirling rate depicts the reflectivity change when Mylar sheet is clean versus dirty. We would need to use experimental data to estimate this, but it would essentially let us estimate how often the heliostat field would need to be cleaned. And the total reflector cost for each subassembly is around $33.03. This is the slide that highlights why the 45-degree incline of the PVC pipe was included to avoid shading when the sun is at low elevation.
All right, so our next subsystem is the electronic subsystem. As you can see, on the left is the full enclosure. As you take the top off, inside we have our microprocessor, which is ESP32. We started out with 12 just because we were trying to find the cheapest option, but found out that we needed a chip of ESP32 to be compatible with the program to track the sign. Also inside there, you have the drivers as well. And so I also did a thermal analysis. That's why you see the fins on the outside for natural convection as well. We found out that the motor actually runs at 5 volts at 150 milliamps, but we were given 12 volts, and the drivers that we have run at 2 amps. Doing the calculations at, I believe it's 13 cents kilowatt hour in Nevada. And then the average time of day is about 10.8 daylight hours, and then add about an hour just for resetting time. We got it to be 18.7 cents per module per day, or $203.49 for the entire field per day to run these. Even though we didn't have to kind of go into the cable or the modeling of it, I looked into finding cables that was water resistant and just like environment resistance. Same thing with the ABS plastic electronics box and the vented overhang of the vents to keep out just the environment, keep those electronical components safe. Well, it's not letting me see that, but the factor of safety for the driver, it's not letting me see that bottom part, but I believe it was around 4, I believe so. Let me check just to make sure.
Yeah.
Just because,
Yeah, 4.7.
okay, 4.7. And I don't know why the bottom is not allowing me to see. And yeah, so the operational factor of safety is 8.4 because we assume 90% efficiency from those drivers. So the way that I did the thermal analysis was following lecture slides that Dr. Trump had posted, and basically it was a complex derivation, but in the derivation it had results for each type of heat transfer, whether it was radiation involved, convection, natural convection, conduction, and in our case, it's just going to be straight convection. There are no fans. There's nothing touching it, so we use convection, and the heat produced, assuming that it's 90% efficient, was 2.4 watts per driver, and we have 5 total for all the 5 motors. Doing that heat transfer, assuming that the thermal shut off temperature for the drivers, I believe, was about 430 Kelvin, which is like 165 Celsius. I used that to find like the maximum heat dissipated, and I got 20.2 watts per heat sink, which is 101 total. And if you go down to the bottom, that's factor safety 8.4. And then just to see where it would start to overheat at, the driver would have to be as low as a 15.8% efficiency for it to start to overheat. For the material selection, the fins came with the drivers, which are aluminum. And then we use the ABS plastic box because as well it is inexpensive. And then the copper wire with the PVC and nylon insulation comes from the wire that I had chosen the later slide. And it also has a lead-free wire jacket, which is environmentally safe.
And here's the assembly time. This is the time it takes to put together one unit. I broke it down into 3 sub-assemblies, starting with the base. You put the gear on the shaft. This doesn't include the pouring of the concrete, but you slide the box down over the shaft, you build the tree, and then you put on the gear bearing mirror assemblies. This is using the Boothroyd and Dewhurst estimation process. I calculated about 12.5 minutes per unit. Hiring 3 workers to build all 1,087 units, it would take around 223 working hours. But it's probably going to be a little bit longer than that. That's if they work straight for 220 hours. But that's that.
So this is the cost breakdown of our design. For off-the-shelf parts, if we're ordering in bulk, it costs $116 per module. If we're ordering per just an individual module, it's $122. The raw materials for the order cost $23, and shipping for a bulk order is $42. Like Tommy said before, if we're using 3 workers to assemble the entire field, it would be $170 per hour. And the total energy cost, which this is focusing on the manufacturing assembly or manufacturing energy cost, is about $15,600 per month. The manufacturing that we have to do is first metal fabrication, which that price is $37.50 per 1,000 parts. And then most of our ABS manufacturing is done in-house with 3D printing. And so as far as overall cost, with shipping, total for a bulk order, it would be $139. And for an individual model, it would be $165. So the key features of our design, we really focused on modularity. We think that being able to assemble it easily is important, while also making relevant repairs, because these heliostats are going to be sitting out in a field for a long time. You want to be able to take a piece off easily, replace a part, fix something, and put it back together. So that's what we really focused on, is in addition to not shading the other mirrors. So there's only one point where it might shade each other, but if you optimize the field, that won't even be necessary. We have a small size ratio where the reflective area is large compared to the support structure and base. That lets us fit more heliostats into a smaller area. Our design is also very durable with the ABS plastic, with the ABS plastic and PVC is coated in a UV protective spray, so the sun won't damage it. And with the gearboxes covering the gear and motor systems, there won't be dust and debris getting into those. And the electronics box is protecting all the electronics. Lastly, it's also very efficient. So we don't have to make an entire field to be able to generate a lot of electricity. So yeah, in conclusion, we found that a few obstacles that we encountered were varying prices that fluctuated our overall cost a lot throughout even working on the project. We also found that more complex actuation systems increase the price even more. So that's why we tried to simplify the actuation as much as possible to reduce cost. And similarly to designing the support structure, picking the right material was really important for us, because we wanted to make sure it would survive while also didn't have a really high cost. So thank you for listening to our presentation today.
All right, awesome. Thank you for sharing your design with us. Do we have questions from our panelists?
Yes, this is Rick Miles from Northrop Grumman. Got a couple of questions. So if you go to your support subsystem analysis, one more slide. All right, so I appreciate you showing where Sigma 1 and Sigma 2 are actually calculated at. I appreciate that. But what I'd like to have seen on both this and the safety slide is an actual free body of how the mirrors are oriented in those particular cases, because I assume that you're applying the forces are being applied via the mirrors. Like I can't tell exactly where you are actually applying the external forces that are then going to get you the stresses at Sigma 1 and Sigma 2.
Yeah, we definitely should have included that. But yeah, the forces are for this one are included are with a flat mirror, and the forces are applied sideways. And with the safety position, the mirror is 90 degrees, and the forces are being applied sideways also. But yeah, we could have included that.
Okay, and then your cost $160, not bad. Then if you could go to your electronic subsystem slide. Can you explain the operational factor safety? I see you say 90% efficiency, but I'm trying to again picture going from a factor of safety of approximately 4.7, and then you go to an operational factor of safety of 8.4. I'm having a tough time picturing the jump between the two.
So with that one, that was a factor of safety from the amount of amps that driver allows versus the amount of amps that we are actually getting through from the source. So that's where that factor of safety from. The actual factor of safety that's needed for like the thermal analysis is the one that's on the next page that talks about how well those fins actually dissipate the heat that's produced by those drivers.
Okay.
And that's the one.
And let's see. I think that's all the questions I have for now. I'll let someone ask. I think there's a couple others, but I gotta go find them. So I'll let somebody else speak while I locate the other question I wanted to ask.
I'll go ahead and jump in. If you guys wouldn't mind, go to your cost slide, please. Actually, we'll start with a good thing. Go back one to your assembly slide. Thank you so much for putting this out there. Very clear. I would have to actually sit and analyze it quite a bit more. But I really appreciate that y'all sat and, you know, really detailed out how long it would take to do each individual thing, because we've had some people that are like, yeah, it'll take 15 minutes. And I'm like, where'd you get that number from? I don't know. We just thought it would take 15 minutes. I'm like, no. So I really, really do appreciate this. Let's go back to the cost slide. Excuse me.
Yeah, I'd like to mention one thing on the previous slide. And we used a quick setting PVC glue. So that's how we could get those times of like 10-second setting.
Mhm. I'm going to trust you on that. I'm not an engineer by any stretch of the imagination. I don't know a thingamajig from a whoosamabob. So I'm going to trust you on that. Okay. For the cost slide. So I will tell you, when I look at this, I'm starting to go cross-eyed, right? Because you're using different, you know, bases and units to compare. So, you know, you have some that are per module, you have some that are bulk order, you have some that are, you know, per 1,000 parts. So what I would highly recommend is taking this. So like the metal fabrication, you know, it's $37.50 per 1,000 parts. Okay, well, how many metal parts per each, you know, module per prototype does this take?
Yeah.
You know, so, and you definitely want to put on your final, you know, you want to put on here, hey, our prototype was, what was it, like $137,
Yeah.
137,
Or yeah, 140 for bulk.
140 for bulk, and 160 something
Yeah.
for prototype.
Yeah.
So I would definitely put that on here, because while yes, it is good to see kind of what all the individual pieces are, I have no way to remember what, you know, the bulk and prototype is.
Yeah.
So,
Yeah.
and like I said, I highly, highly recommend putting on here what, you know, like consistency here, you know,
Yeah,
say it, you know, it was for 1,000 parts is $37.50, but we use X number of parts for this module, so it'd be X dollar amount. You can even have a column that has, you know, process, and then a column of cost for one, you know, for prototype, and then a cost for bulk.
Yeah. Yeah.
So definitely that. So the next thing on here, granted, again, I'm not an engineer, so you'll have to explain this to me. What is additive fabrication?
So that's basically 3D printing.
Okay.
Yeah.
So from what I see on here, you're saying that's free.
Yeah. Well, all of it will be done with 3D printers that we would have.
That you're going to personally buy yourself? I don't think UF is going to let you print out 10,000, 2,000, 1,000, whatever of these for you to go make commercial profit.
Okay, so yeah, I guess we would have to factor in the cost of buying a 3D printer and distributing it between the price per module, and
you know, or you know, look at, people are saying, and granted, again, I may be speaking completely out of my league, what they call it, mold injection, something or another.
Yeah, injection molding.
Yes.
Yeah.
Because 3D printing can get really, really expensive, really, really quickly, not only for the machine, but for the materials. And you've got to have
Mhm.
people that can actually use it and blah, blah, blah. So that, while I like the fact that y'all were like, you know, oh, it's here, we can use it. For prototyping, yes, absolutely. But yeah, I mean, kind of as you see in the
Okay.
comments, like, you know, throw me some of that dough, because
Well,
my
Yeah.
tax dollars are going to pay for that 3D printer that y'all are using to print 1,000 modules to, you know, make your own money.
Well, the reason we kind of started off with that is because I think I was talking to one of the professors, or I heard it somewhere, and they're saying the injection molding is cheap, but only if you're in mass production. Because for a field right now, it would be a lot of money for just to produce or get the machinery for injection molding. And I think they would. I think this might have been Dr. Chesney talking about. I think you're talking about one of the guys who wanted to do Griffiths, I think. He was saying he would like to eventually do injection molding, but for now the 3D printing would have to do just for the prototype base, which is kind of what we're on right now.
Right, but what you're giving me here is dollar amounts for 1,000 units. So you wouldn't be using 3D printing at that point. You know, at this point, now you're talking apples and oranges. You're talking making a prototype for your class for education, and you're talking about making a bajillion so that you can go have an awesome spring break in the Keys, you know? So I understand where y'all are going from this. So it's just feedback. That's all it is. And, you know, I'm a business person, so my brain is wired to think this way. My brain is wired to go devil's advocate on money.
I got a question.
What's up?
So for the future, with just us doing prototypes with any other project that we're doing, in our module, will we include that like 3D printing in the per module, but then when we do the bulk, switch it over into injection molding, or will we take like, is that how we would set up the money wise, like the number, like say we use 3D printing for the
I would
model?
like to answer that. So we would kind of like two cost estimates. One cost estimate for your prototype, which we expect to be way more expensive than your per module in field installation. So we expect to see some cost savings when you go from producing one prototype to producing a huge batch of things.
Okay.
So like if our goal for in use was $100 per meter squared for a prototype, I wouldn't blink at $500 to $600 for a square meter of reflection.
Which I guess was another question I didn't ask. The 146 bulk or whatever it was that the per square meter dollar amount, or is that per module, per bulk modules dollar amount?
Well, that was per module, but each module has 1 square meter of reflective area.
So both. Got it.
Yeah.
Okay.
So it's, yeah.
The other thing I would say, and I really, really appreciate that y'all, again, have the assembly costs. You by far were the best with the assembly costs. I mean, you don't even know how big this is making my heart feel. I'm so happy that y'all went into detail with the assembly costs. But on the other side, you need to look at manufacturing costs too, especially now when you go to bulk. You know, you got labor to manufacture the either 3D printed or mold injection mold, whatever, blah, blah, blah. Again, not engineer, bear with me here. So you definitely want to, you know, throw that into your calculation too. What is it going to cost to have somebody run the machines to, you know, make all of these bits and pieces parts? So that's a small thing. But you know, unfortunately, we have a saying in business that when you come to a project, expect it to take 3 times as long and cost 3 times as much, because little things like this that you never think of. And believe me, I just had a wedding, and let me guarantee you that holds true. 3 times as long, 3 times as much. So, That's it for me. Oh, one more thing. Thank you guys for all dressing up. You all look very nice. It makes it look professional. I would like maybe next time everybody get on the same background, just because then it makes it very easy for me to pick out, okay, who's the team, you know, and it makes it look like you have your act together a little bit more when you're all in cohesion, if you will. Again, it's perspective, it's visuals, but unfortunately it does make a difference. But I really like that y'all are dressed up. It looks like you took it seriously. You know, it looks like whether or not you have your act together, it looks like you have your act together, you know, the whole fake it till you make it thing. So thank you guys very much for that. And I will be quiet now and I'll let everybody else jump in.
Totally unrelated. Somebody just knocked on my door, so I'm gonna get up for a second, but we can continue. Maybe Dr. Chesney can take over for a moment while I grab the door.
Okay, so I don't know if Miles is back with his other.
Yeah, so I do have just two last questions. If you could go to your factors of safety for the actuation subsystem. So you said factors of safety greater than 2, but then I'm looking down at your gears, and your small motor gear, you say experiences a max stress of 8 megapascals, but your yield stress is 13, which
So
yeah.
That's already multiplied by 2. So the force is, I guess I should have made that more clear, but the actual force is around 4 MPa, and then with a factor of safety of 2.
Okay, yeah, I would definitely somehow
yeah.
clarify that. Either put an equation on there to show how you're calculating sigma max, because when I see sigma max, I think of that as the maximum stress that it's going to see.
Yeah. Okay. Yeah, that makes sense.
And then if you could go to your washing cleaning, I forget which slide that's on. Yeah. So I found those particular equations that you gave interesting. I had not seen that before. But my question is, you talked a little bit that the way you were going to wash and clean was with a high pressure spray. Is there any concern about that affecting how the Mylar stays attached to your backing?
Let's see. I guess, yeah, that's definitely a concern. I think the high pressure cleaning, we would definitely have to look more into the specific forces involved with what high pressure is, because I'm sure there's a kind of water velocity that would be optimal for actually cleaning off these modules. But at the same time, the Mylar film and the backing is relatively replaceable. So if you do end up damaging one, it's not that hard to fix. But yeah, we would look into that more.
And that's all I have, other than I did have the same comment that Julia had. I really thought your assembly time analysis was very thorough and very well done.
Thank you.
Okay, so I have just one thing that hasn't been addressed yet. Could you go to your electronics enclosure and tell me about your design for natural convection?
All right, so we had talked about this. I remember I came into you and was just talking about the natural convection. So we did include, at first we only had the vents, like besides the natural convection that the fins have that come with the drivers, on the actual box itself, we included vents on both sides, and they're at 3 different levels. So you do have air coming in from the bottom 2 of the left side, or even the top one on the left side. And as it comes across, the heat does rise and it'll come out on the top side of those other vents on the other side.
Okay, so I'm gonna go ahead and annotate here. So when when air gets hot, it wants to rise up, and there's sort of, is there a way for the air to come out here? Out the top, or is that sealed up real well?
Field.
It's sealed?
Mhm.
Okay, so what it looks like is gonna happen. Let me draw there, okay, it looks like air is gonna wanna come in here because air is coming out this vent up here. So the air is just gonna come in, go right up the side and out the vent. And what we'd really like to see is maybe you got the vents on the bottom on both sides, but maybe if you put the vents further, so like if the vents were further up here, you have one vent up here for the outlet and the vent here on the inlet, then the air has to come in and go across your electronics to go out. And that's sort of the best way to design for natural convection. So think like chimney. Chimneys are tall and skinny and vertical. So if you want a box that is going to help you with your natural convection, you want it like a chimney where it's tall and skinny and vertical, because the natural convection takes advantage of the air is going up. And to get it to have velocity as it goes across your components, you want to force the air to go across the things you're trying to cool down. But yeah, you know, even just ventilation helps, but to really take advantage of the natural convection dynamics, that's how you would design your case.
I mean, it'd make the box design even simpler too, because we only need one inlet, one outlet instead of having 6. Okay.
And I know in some sense it's counterintuitive, like your initial intuition may just be, oh, more vents, more better, but you can actually do better to have fewer vents and force the air to go across whatever thing you're trying to cool down. And Professor Tron, can I hand things back to you?
Thank you.
Yep. Let's see, there's a question in, oh, this might be referring to Dr. Nemi. Is this the guy who thought we disappeared? Is this the guy who you thought disappeared?
Sorry, you're mentioning someone who designed a really good heliostat last time we met, and you said he disappeared, like no one's heard from him, and I thought that was the same name, but it's not.
Oh, no. I didn't get the reference. Yeah, no, no, Dr. Nemi is a faculty member. He's the guy who teaches DML. And he's sitting here staring at me in a very intimidating way. So anyway, are there any other questions from any of our panelists? No? Okay. Then I think we're oh.
Enjoy your weekend, guys.
Thank you.
Thank you all. Well, we'll see some of you in Mech 3.
Yeah, you can't escape. Mech 3 is the required class. So
We'll see you.
yeah, we'll be there. Excited to see what you guys come up with when you have to build a thing. Okay, well then let's stop recording.